Hello viewers, welcome back to the course on matrix computation and its application. So, in the previous lecture we have discussed about the vector spaces and their basis. So, today we are going to start with another thing, that what will happen when we are going to have orthonormal basis. So, that is what we are going to discuss today. So, today we are going to discuss about the orthonormal basis. So, what is that? So, till now we have a vector space, we have discussed with the vector space V that is defined on the given field, and from there we know that we have a basis B that is made up of the vectors V1, V2, Vk. So, this is the basis for vector space V. It means that the dimension of V is k. Now, we know that this is the basis, then these Vi's are linearly independent and B spans V. So, this is what we have seen till now. Now, you have seen that whenever we want to show that for any vector, say I call it x, that belongs to V, if I need to write that x as a linear combination of this vector C2 V2 and Ck Vk, then we need to find these coordinates, and I know that I can write the coordinate of this x with respect to basis. So, this is a C1, C2, Ck. Now, finding these coordinates is a very cumbersome job, because whenever we have a large number of systems, like we have a V with the dimension maybe 10. So, in that case we will, to solve this x and to find this coordinates C1, C2, Ck, we need to solve the system of 10 by 10 matrix, and then with that one we will be able to find this value. So, in fact, in the real life we may have a very large number of a very large system. So, in that case finding these coordinates is really a very tough job. So, to get rid of this one, we take an alternative, and that alternatives we are going to discuss is based on orthonormal basis. So, let us see what is we are going to have from here. Now, so I will start with just simple theory about orthonormal basis. So, suppose we have two vectors V1 and V2. So, that belongs to the vector space V. Now, I will say that V1 and V2 are orthogonal to each other. It means that if I take the dot product V1 dot V2, so this is we are talking about dot product, or I can also call it inner product. So, if I take the dot product of two vectors, and if this is going to be 0, then we say that these vectors V1 and V2 are orthogonal to each other, and also we call it. Now, based on this one, I know that we can find the magnitude of the vector. Sometime we also write like this one. So, this is a basically a symbol of norm. So, this is we can represent by V1 taking the dot product of V1 itself, and then taking the under root. So, that is the basically magnitude of the vector V1, or we also call it length of vector v1 or magnitude of vector v1. So, what do we do that? Now, I take any vector v1 and I will divide by its magnitude. So, now whatever the vector we are getting, so this will be can be written as hat. So, this is called normalized vector. So, it is a normalized vector, and if you see now, then its length is 1. So, what we have done? We have taken a vector, divided by its magnitude. So, that process is called the normalization. So, we have normalized the vector and then its magnitude become 1, and this vector v1 and v2 already was orthogonal. So, now from here v1 and v2. So, now what I do is that now if vector v1 and v2 are orthogonal, first one, second, and v1 magnitude is equal to 1, that is equal to v2 magnitude is 1 or the length is 1, then from these two we call it that set v1 and v2 is an ortho coming from the orthogonal, and normal means it is normalized. So, it is called an orthonormal set. Okay. It means the set, the v1 and v2 are orthogonal and their magnitude is 1. So, then it is called orthonormal set. Now, the question comes that how we can talk about the basis. That, so for example, suppose I take a vector, for example, I take a vector, we talk about R2, then let I take v1, one vector, and I suppose I take 1 minus 1, and v2 I just take 1 1. Now, if you take the magnitude of this vector, so it is 1 square plus minus 1 square under the root, so it is under root 2. So, it is its magnitude is not 1. Similarly, if I take the magnitude of v2, that is also under root 2. Now, I divide by this one, so maybe I can call it u1 now. So, u1 is, I will take the v1 and divide by under root 2. So, it is 1 by under root 2 and minus 1 by under root 2. And similarly, I can construct my u2. So, that is 1 by root 2 and 1 by root 2. So, these two vectors are normalized now. This is normalized vectors. Also, now I just check what will happen to, so there is no difference between orthogonality. Now, what I am going to do is that I will check from here v1 dot v2. So, if you see from v1 dot v2, we are taking the dot product. So, dot product is component wise. So, I will call it 1 into 1 plus minus 1 into 1. So, that is 1 minus 1, that will be 0. Or I can write from here u1 dot u2. So, that is 1 by root 2 into 1 by root 2, the first component multiplying, plus minus 1 by root 2 into 1 by root 2, and that is 1 by 2 minus 1 by 2, and that is 0. So, in this case we can call it that these two vectors, so vectors u1 and u2 are orthonormal. It means they are orthogonal and their magnitude is 1. So, now from here this is become the orthonormal set. So, this dot product, if you see from here, then this dot product I can write in this form also. So, this is in the vector form, we know that how to take the dot product, but what I can do is that I can write this dot product in terms of matrices, because we know that the matrices. So, V1 is the vector, so I call it, because a vector V we always take in the column form, like this one we have taken, and V1 transpose if I take, that will be a row vector. So, this dot product I can write as V1 transpose multiplied by V2. So, this is basically matrix multiplication. So, I can write from here that what is V1t? V1t will be a row vector. So, this is 1 minus 1, and V2t is 1 1 column vector. So, this is the matrix of 1 cross 2, and this is a matrix 2 cross 1. Now, if I multiply these matrix, so this will multiply by this one, so it will be 1 minus 1 and that will be 0, because we know that this is orthogonal. So, this dot product we can also write in this form. So, that is the matrix multiplication, and this is a vector dot product, but the things are same. So, after doing this one, now the question is that now from here I can say that this V1 and V2 are orthonormal vectors. Then what about linear independence? The question is that is the set V1 V2 linearly independent? Because if we discuss about the orthonormal basis, then we know that it should be linearly independent. So, let us check that whether this V1 and V2 are linearly independent or not. Okay, so, this one I can just check. So, by contradiction we can say by contradiction. So, let V1 and V2 are linearly dependent LD. It means if one vector, so I can write vector V2 I can write as a some scalar multiple of V1, where alpha is not equal to 0. Okay. So, I am taking V1 and V2 any orthonormal vectors. So, it means that V1 is 1 and V2 is 1. So, I can say that let V1 and V2 are orthonormal vectors. Now, so this is I have written. Now, I take the dot product V1 dot product V2. So, I can write here V1 dot product alpha V1, because V2 is alpha V1, and from here I can take this alpha common. So, it can be written as V1 dot V1. Now, from here I can write this as alpha and V1 magnitude square. So, but V1 and V2 are orthonormal vectors. So, I know that it should be equal to 0, because V1 V2 are orthonormal. So, from here, which implies that alpha and v1 square, that should be equal to 0. Now, we know that alpha is not 0. So, neither alpha is 0 nor, so if I take the magnitude is equal to 0, then we know that its magnitude is 1. So, I can say from here that this magnitude is neither alpha is 0 nor v is 0. So, from here I can say that, which implies that v1 and v2 cannot be linearly dependent. So, from here we can say that the vector v1 and v2 are linearly independent. It means if I take the vectors, two vectors which are orthonormal, then definitely they will be linearly independent to each other. So, this is a very important result of the linear independency. Now, so the question comes that suppose we have a vector space V over the field F, and so this is a vector space, and now from here I call it finite dimensional. So, suppose its dimension of V u is n. So, it is a finite dimensional space over the field F. Now, what I do is that I take a basis B u1, u2, un. Okay. So, let this is an orthonormal basis of vector space V. Okay. Because here we are talking about n dimensional vector space and I am taking the basis of direct this one. So, we are talking about the square type of matrices, but it can be suppose if I take the dimension of u is n and if I take the bases which contain the vectors less than n, then you know that this basis will create a subspace of V. So, but now we are taking that it is an orthonormal basis of vector V. Now, from here, so which implies that B is linearly independent also, and which also implies that ui dot product uj, that is equal to 0 when I is not equal to j, and if it is same elements then it will be 1, because it is an orthonormal basis. So, that is there. Now, I want to see that, because we know that this is a linear independent. Now, what is going to happen now? Let us check that how it is useful for finding the coordinates. So, let we take any vector x belongs to the vector space V. So, then I can write as x can be written as linear combination of C1 U1, C2 U2 and Cn Un. So, I can write this linear combination because these are bases, and I know that this will be uniquely determined. So, we need to find the value of C1, C2, this one. So, I can call it 1. Now, so it is a vector. So, I want to find C1, C2. So, for this one what I know I will do that. So, I will define the x, this vector, taking the dot product with u1. I define like this one. So, it is a dot product of x with u1. So, x is this one. So, I can write it Cu C2 U2 Cn Un. So, this is my vector taking the dot product with u1. Now we know that in the dot product, suppose I have a vectors u plus v, taking the dot product with w, so it can be written as u dot product w plus v dot product w. And I also know that alpha, we are talking about the real scalars, so alpha u taking the dot product with w, that can be written as uw. So this is real scalars we are talking about. So that we already know this property. So from here I can write like this one. So this will be equal to C1 U1 U1 taking the dot product plus C2 U2 U1, and I can write from here Cn, this will be Un taking the dot product with U1. Now I know that this is the orthonormal basis. So from here I know that this is 0, this is 0. So all other term will be 0 except, so this one can be written as C1, and this is U1 taking the dot product of U1. So I can write from here that this is equal to U1 square. Now I am taking the orthonormal basis, so this quantity is 1. So from here I will get C1. So from this I can say from this that my C1 is taking the x dot product with U1. So that is my C1. Similarly, to find C2, what I do, I take the dot product of x with U2. So it is the same way will go, it is C1 U1, C2 U2 and Cn Un taking the dot product with U2. So ultimately if you see from here the same way will go, then we will get C2 U square, only left with this one. All other terms will be cancelled out the same way because they are orthonormal basis. So this means the orthonormal basis means that if you choose any two vectors from here, different vector, their dot product will be 0, and if you take the same one, so it will be 1. So that is the meaning of this orthonormal basis. So from here I will care that my C2 is x dot U2. So from this way I can find, so similarly I can find so in the similarly we can have or we can find C3 is equal to x taking the dot product with x3, C4 is equal to U4 and so on. Cn will be taking the dot product of x with Un. So from here now this equation 1, so equation 1 can be written as, I can write x. Now C1 I know it is x into U1, so I can write from here it is x dot U1 plus x dot U2 plus x dot product with Un, this is equal to Un. So by this way we are able to find the coordinates of a vector very easily, because here just we are taking a dot product and that's it, we are able to do that one. So now from here you can see that my coordinates of x with respect to the basis are simply x dot U1, x dot U2, x taking the dot product Un, this one. So, this is the advantage of dealing with the orthonormal basis. So, let us take one example. So, in this example I will just take some orthonormal basis. So, let us take I take a vector space R cube and I choose the basis. So, I just take V1 I will take 0 1 0, V2 will take minus 4/5 0 3/5 and V3 we are taking 3/5 0 4/5. Okay. So, this is a vector I am taken from here. Now, you can see from here that V1 if you see its magnitude is 1, V2 is also its magnitude is 16/25 plus 9/25. So, it is 1. V3 that is also 9/25 plus 16/25 under root. So, that is equal to 1. It means these are normalized vector, and also you can see from here that V1 dot product V2 is 0 plus 0 plus 0, that is 0, the first two vectors component wise dot product. Now, V2 V3, so that will give me minus 4/12/25 0 plus 12/25 and that is 0. Similarly, V1 dot V3 if you take, then this is 0 plus 0 plus 0, that is 0. It means that these vectors are orthogonal to each other. So, they are mutual orthogonal and their magnitude is 1. So, I can say that these are the orthonormal basis. So, this is, I can call it orthonormal basis of R3. Now, suppose I choose, so let us take one. So, let us say consider a vector x from R3. So, I call it suppose 1 1 I take, that belongs to R3. Now, I want to find x C1 V1 plus C2 V2 plus C3 V3. So, now I know that my C1 is basically taking the dot product of x with V1 and x is my 1 1 1 taking the dot product with 0 1 0. So, if you see from here, then it is 0 1 and 0. So, it is 1. So, my C1 is 1. C2 x taking dot product with V2. So, it is 1 1 1 taking the dot product with minus 4/5 0 3/5. So, it will be minus 4/5 plus 3/5. So, it is minus 1/5 and my C3 will be taking the dot product. So, it will be 3/5 0 minus 4/5, not minus, it is plus. So, it will be equal to 3/5 plus 4/5, that is 7/5. So, from here you can say that my x is equal to V1 minus 1 by 5 V2 plus 7 by 5 V3. So, this is the linear combination we can write, and these are the coordinates we have taken. So, from here the coordinate of x, or maybe I can just call it that coordinate of vector 1 1 1 with respect to the, so I can call it this as a basis, orthonormal basis. So, I just call it B. With respect to B is just 1 minus 1 by 5, 7 by 5. So, that is the answer of this question. So, it is very convenient for us to find out the coordinates or the vector x with respect to the orthonormal basis. So, that is the one of the advantage of taking the orthonormal basis. Also, if you see from here, this orthonormal vectors if I am taking. So, what I am going to do is that I will make a matrix made up of this basis. So, I just take here V1 first column, then V2 and V3. So, I write this matrix. So, it is 0 1 0 minus 4 by 5 0 3 by 5, and then in the last it is 3 by 5 0 4 by 5. So, this matrix we have taken, I call it matrix maybe U. Now, if you see from here, we have already seen that these columns, these vectors are orthonormal. So, it means that if I take the dot product of these columns, then this is going to be 0. So, this vector I can, from here I can say that this is my column 1, column 2, column 3. So, if I take the dot product of these columns, so these columns are mutually orthogonal. Columns are mutually orthogonal and their magnitude is 1, that we already know. Now, we call it R1, R2, R3, this row vectors. So, why now we are calling the row vector. So, what about this one? Now, if you see from here, this 0 minus 4 by 5, 3 by 5. So, if I take the dot product of R1 with R2, so if you see from here, it is 0 plus 0 plus 0, so that is 0. I call it R1 dot R3. So, R1 dot R3, that is 0, and then from here it is minus 12 by 5 and it is plus 12 by 5. So, it is again 0, and R2 dot R3 if I take, then it is 0 plus 0 plus 0, that is 0. So, it means that in this case my columns are mutually orthogonal to each other, as well as the rows are also mutually orthogonal to each other. So, such type of matrix if you get, then from here you will see that U is an orthogonal matrix. So, what is the orthogonal matrix? So, orthogonal matrix is that in which the columns are orthogonal to each other and rows are also orthogonal to each other, and the magnitude of each columns is, or the rows is 1. So, that is the definition of orthogonal matrix. So, this is the orthogonal matrix, and now from here, starting with the orthogonal matrix, what I am going to do is that, so orthogonal matrix I am taking. Now, if you see from here, U transpose U. So, this is what we are going to find out. Now, U transpose will be this one, So, taking these, so it will be 0 minus 4 by 5, 3 by 5, 1 0 0 0, 3 by 5, 4 by 5, and then taking the u itself, by 5. I am taking the dot product. So, if we just take the product of this matrices, so this is this, so it is going to be 1, because this will the same vector we are multiplying. Now, the first column and this second row is 0, this that is also 0. Now, from here the same thing I am going to do here. So, it will be 0, this vector and this vector are same. So, its magnitude should be 1, these are orthogonal 0 0 1. So, it is my identity matrix of dimension 3. Now, the same thing I can verify that what will happen if I take u transpose. So, in this case, if you see, then this is my same matrix. I can write here once again 0, 3 by 5, 4 by 5, and it will be 0 minus 4 by 5, 3 by 5, so if I multiply this vector with this vector, so it is 1. Now, this vector multiplying by this row, so it will be 0, so it will be 0 0, then 0 1 0 0 0 1. So, from these two you can see that, which implies now that u transpose u is equal to I, and that is also equal to u transpose. So, this is possible. So, from here I can say that the inverse of u, that is equal to u transpose. So, that is another advantage of dealing with the orthonormal basis, that whenever we have a matrix made up of orthonormal bases, then in that case if we want to take the inverse, that is just the transpose of the given matrix. So, it is also very easy to find out the transpose of a matrix as compared to finding the inverse of the matrix. And from here also I just want to find the determinant of this. So, if you see the determinant I want to find, so it will be 0 1 0. So, I can just, it will be minus 1, I just take this one, going from the first row, I am first column. So, it is, I am taking this one. So, this and this. So, it will be minus 16 by 25, minus 16 by 25, because I am considering this minus. So, minus and minus, minus 9 by 25. That becomes minus minus 25 by 25, and that is 1. So, from here you see that this is equal to 1, and these things we can check from here also, since u transpose u is equal to I, and we know that matrix u transpose taking the determinant is same as the determinant of the matrix. So, from here if I take the determinant of I is 1 always. Now, if I take two matrix and determinant that is equal to determinant of A and determinant of B. So, that should be equal to determinant of square, that should be equal to 1, and from here I can say that this is equal to always this one, plus minus 1. So, it means that the orthogonal matrix are always having the determinant either plus 1 or equal to minus 1. So, this is the some properties of the orthogonal matrix that is made up of the orthonormal basis. So, that is why this matrix is called the orthogonal matrix. So, I will stop here. So, today we have discussed about the orthonormal vectors and orthonormal basis, and then we talk about the orthogonal matrix. So, we will continue with this one in the next lecture also. So, thanks for watching, thanks very much.